Derive the equation for two generalized analogy in transport phenomenon. Reduce this to Reynolds analogy and Chiltern-Coulomb analogy. Write all the limitations for using those analogies. You can see the physical interpretation of frictional factor, which is half into F into Reynolds number equals to length of sheet divided by film thickness. Then you can see the physical interpretation of heat transfer coefficient, which is equals to heat transfer coefficient equals to thermal conductivity divided by film thickness. Next you can see the physical interpretation of mass transfer coefficient, which is equal to Kc equals to mass transfer coefficient equals to diffusivity divided by film thickness. Next you can see the Nusselt number is equals to H, which is the heat transfer coefficient, into LCT length of sheet divided by K thermal conductivity. Next you can see the Sherwood's number, which is given by the formula in 5th number equation. Next, substituting 2 in 4, we get the equation in terms of LCH divided by delta T. Then substituting 3 in 5, we get the Sherwood number relation, which is given in equation number 7. Examining equation number 1, 6 and 7, we get interface flux divided by molecular flux equals to characteristics length divided by effective film thickness. Then we get effective film thickness equal to diffusivity divided by transfer coefficient. Using equation number 1, 6 and 7, we get the relationship of the length of the sheet in terms of the following given formula, which is given in equation number 10, where LCH equals to half frictional factor into Reynolds number into film thickness equal to Nusselt number into film thickness equal to Sherwood number into film thickness. Substituting Nusselt number formula and Sherwood number formula in equation number 10 gives the following relation, which is equal to half frictional factor in the film thickness to standard number of heat transfer into Prandtl number into film thickness equals to standard number of mass transfer into Schmidt number into film thickness. Now comes the Reynolds analogy. Similarities between the transport of moment of energy and mass were first noted by Reynolds in 1874. He proposed that the effective film thickness for the transfer of moment of energy and mass are equal. Therefore, equation 11 becomes this, given by the equation number 12. Reynolds further assumed that Prandtl number and Schmidt number is equals to 1 under the circumstance. Equation 12 reduces to equation number 13, which is also known as Reynolds analogy. Physical properties of equation number 13 must be evaluated at T average, which is the average of wall temperature and interface temperature. Now comes the Chiltern-Coulomb analogy. In Chiltern-Coulomb analogy, the relationship between the effective film thickness are expressed as follows. Substituting this in equation number 11, we get the following equation number 14 and 50, which is given, where equation number 14 is given by F by 2 equals to standard number of heat transfer into Prandtl number to the power 2/3 equals to JH, and equation number 15 is given as follows, equals to F by 2 equals to standard of mass transfer equals to Schmidt number to the power 2/3 equals to Jm, where Jh and Jm are Coulomb J factor for heat and mass transfer respectively. Physical properties of equation number 14 and 15 must be evaluated at the average temperature. The Chiltern-Coulomb analogy is valid when Prandtl number is between 60 and 0.6 and Schmidt number is between 3000 and 0.6.